think I do. Okay. So I am coming to you from a completely empty office here in Oregon. I'm at Intel. I am going to share a little bit of some details for a new AES-XTS implementation that was added to OpenSSL in 3.5 earlier this year. A little background information about myself before I get started. This is actually my second stay at Intel. I was away for about 4 years where I worked in the automotive industry, actually, and came to be acquainted with like high assurance and safety critical software, and found myself really working at the intersection of math and computer science. And I really enjoyed it. And so when that time in startup land came to an end, as startup land jobs often do, and I returned to Intel, it took me a little while to find that niche back here. But about 2 years ago, an opportunity kind of fell into my lap that is very similar to the one that I'm going to share with you today, but it was about RSA instead of XTS. And so when the work that I want to share with y'all came down the pike, I volunteered. And so this presentation basically covers everything I learned along the way as we were getting this ready to contribute to OpenSSL. Before I get all the way into it, as I was putting this presentation together, kind of at the last minute, I added this slide because there was a couple of optimizations that I wanted to be able to cover that were not strictly vectorization related. There's a couple at the very end, and I thought they were really interesting, and I wanted to be able to show off some of my coworkers' work. So I wanted to generalize our sort of guardrails. I'll start with a little bit of a roadmap. We're going to go into some details about AES, where it comes from, how it works. Then we'll do the same sort of deep dive into XTS. And then I will give a bad and contrived example of vectorization from a theoretical standpoint, and we'll use that to then talk about it from a practical standpoint. And then we will look at all of this context that we've used so far to actually look at how we do these vectorization optimizations in practice using the XTS implementation that is actually in OpenSSL right now. We'll kind of move back and forth between an x86 implementation and a reference implementation that I put together in Haskell as I was doing this. The intention there being that I can write it in Haskell and it can hew very closely to the original standard. It gets very close to the math that we find in the standard, and then we'll go back and forth so we can kind of see what it looks like when we're trying to be as close to the standard as possible, and then what the optimized version of it looks like when we're writing it in x86 assembly. So first, we'll talk a little bit about AES here. I would imagine that most everybody in the room already knows a lot of these details. It's almost a 25-year-old standard. It's symmetric key, so something else has to happen before. If we're talking about this in the like Alice and Bob context, both Alice and Bob have a copy of the same key, and they have to use something like RSA to exchange those keys before they can begin this communication. It's the underlying technology that's used in things like SSL and TLS. AES comes in 3 different flavors. The only difference between these 3 flavors is the bit width of the key. And the first step along the way in AES has to do with expanding that key into 16-byte chunks. And we call these the round keys. And when the algorithm is run, depending on the width of the original incoming key, it just gives us a different amount of round keys. So we're looking at this for 128 bits, we end up running 10 rounds. If we do this for 256 bits, we end up having 14 rounds. In OpenSSL and in the XTS implementation that we'll look at later, we only have an implementation for 128 bits and 256 bits. But the standard for AES actually includes all 3. Okay, so this is a very high-level implementation of the encryption side of AES. So what we're looking at, if you look at the very last line here, we are recursively running this round function that you see here. And when we get to, and we're increasing the iterator as we go. So when we get to 14, we're done. So this is a 256-bit implementation of AES. The round function is run iteratively, stepping through 16 bytes of that expanded key at a time. So that's what we're doing. We're taking 4 32-bit words from the expanded key, And then when we iterate, we drop the 4 that we just used. Round key, or the round, just runs these 4 transformations where we have subbytes, shift rows, mixed columns, and add round key. The final round elides the mixed columns step. So we have a special function for covering the last round. And so you'll see here when we reach the 14th round, we're using the last round function. And this is the base case, so we're done. So we can look at this in x86 assembly as well. So this code is using Perl-asm that we get from OpenSSL. So what's behind these $ variables is a vector register, and I will cover details about the vector registers when we get there. But you can just imagine this is just a like %sign ZMM or YMM register that we're looking at here. So the first step in the algorithm is the add round key step. This part is literally just XORing the key into the state, which is just a 16-byte block. And then we run 10 rounds. And so that entire round function that we were looking at before is implemented in a single instruction on x86. That's what this VAES-ENC is. And then we have the special case for the last function, or the last round, which does not include mixed columns. So this that we're looking at here is exactly the same implementation, but done in x86 assembly. Okay, so now we can look at some technical details for XTS. The XTS full name is XOR encrypt XOR with cipher stealing, defined in IEEE 1619. It is a confidentiality only mode of operation for AES. I have here that it's the standard encryption used for data at rest. IEEE 1619 is not titled like XTS or XOR encrypt XOR. It actually has a name like something to the tune of encryption for block-oriented storage devices. So it was originally created for encrypting data at rest for disks. In its simplest form, XTS is literally we XOR this incoming value that's called a tweak. That's what the TWK variable is here. We then run a full AES encryption, like all 14 rounds of it. And then we do XOR again with that same state that has now been encrypted with that tweak value. And I'll cover some details on what the tweak is here in just a second. So if we look at this same implementation in x86 assembly, we're doing the same thing. We XOR that key in, we run the 14 rounds of AES encryption, and then we XOR the key a second time. And the same story here. Behind these $ variables are these vector registers. Okay, so the tweak is the initialization vector that comes in at input for encryption and decryption. The standard actually recommends like using a device ID or something like that. But when we implement this in OpenSSL, there's just some random bytes that come in. It goes through an AES encryption step at first, and then after that, it gets updated between each block. So the point of a mode of operation, I imagine that everybody in the room knows here, it allows us to be able to do more than 16 blocks at a time because AES is limited to, like the standard is limits us to those 16 bytes. So if we want to be able to do more than that, we use these modes of operation to chain together many AES rounds. And so in between each of those AES rounds, we have to update this tweak value as it gets XORed into the pre-encrypted and then encrypted values. So this algorithm is how we update the tweak. It's a 128-bit value that just gets shifted to the left by 1. If that shift is going to overflow, it gets XORed with this constant value that's found in the standard, this hex 87 byte value. Otherwise, if the shift left is not going to overflow, it just shifts left and we're done. The other detail that has to be covered for a mode of operation is to be able to work with input like sizes, byte sizes that aren't evenly divisible by 16. So what you're looking at here is the cipher stealing piece of XTS, or a visualization of it. What happens when we get to the final complete block when we're doing encryption is we first encrypt that final block, and then we take those dangling bytes and they get moved to the front of that complete block, and we run encryption again. And in between these two steps, a new tweak is generated. When we do this on the other end, we do it in reverse, and it's a little trickier. So we're looking at decryption here. I highlighted the tweak details. It's kind of small, but I highlighted the tweak details in red because it's an important one. When we're doing this on the decryption side, when we reach that final block, the tweak that we have in hand, we actually need to generate a new one. So we have a new tweak that's like twice removed from the previous one that we had used. When we do the same swap and we do decryption using that one that's twice removed, and after the swap, we use the one that we had in hand when we got here. So this is literally this routine from encryption in reverse. And this is how we are able to decrypt that data using the same inputs. Okay, so that is most of the context that we needed to set for the algorithms before we can get into the details about vectorization and then looking at the optimizations that actually appear in the XTS implementation that we're here to talk about. There were a couple of things that I wanted for us to keep in mind before we moved on. And these are the algorithmic characteristics that surface in both AES and XTS. I kind of blew through this at the beginning, but AES is limited to these 16-byte blocks. When we're thinking about it, like block A to block B, like there's no relation to them whatsoever. It's completely limited to these 16 bytes. XTS does its best to preserve this relationship. It's only when we get to the very end of a chunk of data that we're trying to encrypt or decrypt do we have any dependency on the previous block. So those are things that we want to keep in mind as we move forward to look at how we do optimizations for this. Okay, so what is vectorization? Its simplest form is we're just doing the same instruction on several scalars that are loaded into a single register. So we want to do something like addition, which I'll cover here in a second. We can just take 4 values, let's say, and just do that addition on all 4 values in a single instruction. In practice, on x86, we have these different sets of registers that are mnemonics for how wide they are. So the XMM registers have 128 bits. YMM registers are what we get from AVX2. It has 256 bits. And then the VMM registers have 512 bits. So this is what we use for AVX512 that we get starting in Ice Lake timeframe. And so the implementation that we're going to look at here at the end originated in Ice Lake, but we actually didn't add it to OpenSSL until after the Sapphire Rapids generation. The instructions themselves have these prefixes and postfixes to kind of denote what the data type is and to make sure that we're aware we're working on a vector instruction. So this is the add instruction. You can see here that we're denoting we're working on a vector. It's packed 64-bit integers that we're working on. So the second prefix and that postfix there are a part of the data type declaration, and then the operation is what we find in the middle. So if we were to use this instruction for these registers, where the value that we found in YMM0 was this V register, and the value that we found in the YMM1 was this W register, then we're just adding them together. And so what we find in YMM1, which is our destination register, is this vector 6, 8, 10, 12. Pretty simple. So when we're looking at these things, and the things that I wanted to keep in mind when we started here was that if I had to distill down a set of properties that we're looking for when we're doing these types of optimizations, the first one, which is the simplest, is this idea of data independence. The AES blocks don't depend on one another. XTS does its very best to preserve this relationship, so there is no dependency. And this is kind of what I mean by data independence. Since the blocks are not related, we can parallelize the encryption or decryption of several blocks at a time. And the second one is a little bit more complicated, and this is not a perfect term for it. And I will give an example for what I mean, but this is the idea that if a function is linear, then we can generate its outputs in chunks or steps along the way. Like an increment, if we are doing like an incrementation, we can go ahead and load the register with, say, the first 4 outputs of that incrementation, and then we can increment each element in the vector along the way is one example. And so the final optimization that we'll look at uses this linearity, and I think it will make more sense when we get there. Excuse me. So here, we're looking at a kind of scrubbed implementation of the XTS implementation that was added to OpenSSL in 3.5. We begin by broadcasting this key value. So that is the encryption key that we're working with. So all of the blocks are using the same key. And so the broadcast instruction is taking something from a regular scalar register and putting it into all lanes of the vector register. So what we have here is now the value that was in that key 1 register is in all 4 lanes of the register that's behind this T0 variable. This turn log instruction, the first constant value is telling us what ternary logic operation we want to do. This x96 constant is just doing XOR. So this is the add round key step for the AES, for AES. Then we go through 14 rounds of encryption, and then when we're done, we have we're moving the values that were in that state 1 register to the output register. Now, what's behind each of these is a YMM or ZMM register, and we actually have 4 AES blocks in a ZMM register behind this variable. And so when we're doing this encryption, what's in the tweak when we do this XOR is actually 4 different tweaks. So we can go through 4 different blocks at a time. So that's what's happening here. This is the vectorized implementation. We're running through 4 blocks at a time instead of just 1. But we're not limited to that. Because we can generate these tweaks in this way, we can actually parallelize not just on a single instruction level, we can actually grow this out to doing several instructions. So the actual implementation that is in OpenSSL doesn't do this 1 or 2 times. It actually goes up to 4. And we'll cover some details on why we are able to do this parallelization even at the instruction level here in just a minute. But we're not even limited to 4. We stop at this for a reason that I'll show in just a minute. But the idea to show here is that because these blocks are fully independent, we're almost unlimited to the from a theoretical standpoint on how deeply we can parallelize this. So here is the linearity example that I wanted to share to try and make that a little bit clearer. When we're working with these tweaks, it has this kind of gentle notion of linearity. If we're generating this T prime from the incoming tweak T, we can actually generate a T double prime, a second tweak, by adjusting the arithmetic that we're using to generate the tweak. So this means that if we can set things up in such a way, we are able to actually generate enough tweaks to fill an entire vector register from a single one. And fill all 4, and then that's how we are able to do these parallelizations. But we saw before, we're actually doing this with 4 instructions at a time, which means that we need to hold 16 tweaks. And so one of the optimizations that we'll look at here in the end shows how we are able to generate that many tweaks, all from the single incoming one. So this is the simplest version. What we're looking at here is generating 4 tweaks, starting with the one that is in ZMM0. These constants have the shifts in them. So we were looking at it before that we can shift by 1 to get tweak prime. We can shift by 2 to get tweak double prime. This constant that we're finding here is doing a left shift. That's what this instruction does of the value that's here in ZMM0, putting it into ZMM4. This one is the same instruction, but right shift. And so this is capturing any of the overflow bits that we would have from ZMM1 into ZMM2. And then this instruction is a carryless multiply. This allows us to use that, so this is Z-poly here is that hex 87 value that we were looking at before. So when we do this, this allows us to not have to do any branching. As we bring those carry bits over back into the least significant positions, we can go ahead and do this multiplication. And if those bits are all zeros, then the multiplication leaves them as zeros. But if they're ones, we do a carryless multiply, and we're able to have that same kind of XOR relationship without needing to carry or worry about the overflow bits, or have any sort of conditional here where we have to check to see if there's any overflows and then do it. And then these two instructions are putting the newly generated tweaks all back together. Is what we're doing here. We're XORing the top half and the lower half together. Okay, now we can look at a couple of the optimizations that were not strictly vectorization related. The first one I already alluded to a little bit. This is the idea of being able to do these instructions in parallel. Now, the reason why we do 4 here is because these instructions are pipelined. And the way that we can compute the number of instructions that we want to issue is by thinking about how many cycles in like the latency is. So you can think of as a cycle as a step along the pipeline. This is not exactly how it works, but it's a good abstraction to use. And then the number of ports that can actually receive these instructions is, so in the perfect case, the ideal number of instructions per cycle that we can accept is what IPC is here. So if it is a 4-cycle latency, we have 2 ports that can accept those instructions, then we want to issue 8 at a time. And we have a little visualization of how this works. So you can imagine that when we issue the first 2, the first step in the pipeline is occupied, and then we issue 2 more, and now the first 2 steps are, and then as we get our way through, now we've issued 8 instructions, and that pipeline is fully saturated. So this is why we issue as many as we can, but the reason we actually stop at 4 in this case is because there is a sort of like a diminishing return scenario where you begin to have register pressure, and it is no longer, you stop seeing the same results, and it becomes a kind of like binary search, like how far can we parallelize this before it starts to have detrimental effects. And so we stop at these 16 blocks at a time by issuing 4 instructions at a time. So another interesting thing about looking at instruction level parallelization, we were looking at this one, thinking about the pipelining here, and thinking about the pipelining here. But while we're doing this, in between rounds, we also issue these instructions to generate the next set of tweaks before we begin the next round. And this is for 2 reasons. One is that the ports that on the CPU that these instructions are using is a different set of ports on the CPU than these instructions are using. And these registers are independent from the registers that are being used here. So the CPU can actually issue these blocks in parallel. And so we're able to saturate these ports at the same time that we're saturating these ports. And so that's why we do these kind of interleaves along the way. And so this is exactly how it appears in the implementation that was contributed, where these blocks of tweak generation happen in between rounds so we can saturate all of the ports on the CPU. And so this is the very last one. I think it's the most interesting. What we're looking at here is actually fully saturating even just tweak generation. So here we're generating 8 tweaks, all based off of the incoming one that's in ZMM0. And we're doing that by doing a completely different set of registers for tweaks 4 through 7 than we're using for 4 through 3. And that is possible, made possible by the fact that our constant values here have a different set of shifts. So this one is shifting by 0, 1, 2, and 3 on each lane, but this one is shifting by 4, 5, and 6, and 7 on each lane, all based on here. So this is generating the first 4, this is generating the second 4. And so now we have 8 tweaks in hand, but we're able to issue these in parallel because none of these registers have any dependency on one another. So I think this one is really fun too. And this is the one, this actually was the last one I added. It's why I wanted to change the title of the presentation. I think that's all. Yeah, that's actually all of the content that I had. But I wanted to make sure that we had plenty of time for any questions or anything like that. So I think I will stop there, see if there's any questions in the room. I'm sure there's some experts here that can tell me I missed something or something like that.
So my question is about compilers. So if I will have my C program and I will want to some vectors, does compiler on normal O1 optimizations use these vector packed add, for example?
No, I think in most cases it doesn't. There is not a great automatic way to do a lot of this, and it still has to be done by hand, like this handwritten assembly here. Now, the compilers do have intrinsics for a lot of the instructions, so you don't have to write this in assembly. If you wanted to get access to these, you can use the intrinsics. But in most cases, these type of optimizations still have a human in the loop, and being able to do it automatically, I think, is still kind of an open problem in lots of cases.
And one follow-up question, like for Intel and AMD processors, is it somehow standardized, like these instructions, or it's different, animals?
It is standardized. Yeah, I think that all of these instructions are actually on both sets of hardware. Both sets of architecture, or the same architecture, have the same instructions. Yes.
Thank you.
Mm-hmm.
Hi. This instruction that you showed, the AES-Inc. does the AES round, is that AES specific extension to x86 or AVX?
Yes. It comes with a product called AES-NI, which is the AES new instructions, is how Intel names these things. And so the ones that I showed that are vectorized, the product is called VAES-NI. But yes, it's an extension to the x86 ISA.
Thank you.
Mm-hmm.
Hello, thank you for the talk. Recently, I do a lot of vectorization in my job. It's not cryptographical, but something similar is shown. And I'm interested, what do you use for analysis of effectivity of the code, like you shown saturation of the ports and so on? Do you use vtune, or do you have other tricks? How you guess these things? How you work with this?
There is yes. A lot of it is actually done using just what we have available. So a lot of this implementation was done just by benchmarking using the speed tests that ship with OpenSSL or with AWS-LC, which is where my primary day job is in AWS-LC. But there are internal proprietary tools that are used to do this kind of thing as well. But in a lot of cases, you can see some of these details by using the Intel specific stuff that shows up in Linux perf. So Intel has a thing that was originally written for vtune called TMA. It's the top-down methodology analysis. And a lot of that stuff has been contributed to perf. And so if you look through the events that are made available through TMA in perf, you can see some of the instructions retired per port and that type of thing that you could use to see if you were saturating these, et cetera. But in the case that this was done for knowing we wanted to stop at 4, I think it was really just looking at the final throughput and being okay, I'm starting to see some degradation here, so we're going to stop at 4.
Thank you.
Mm-hmm.
Any other question from the audience? We have still last 2 minutes. If not, we. So there's a question. Okay.
How much speed up do you get in practice? So do you get this factor of 4 for vectorization?
Sorry, could you say that one more time?
So how much speed up did you get in practice?
Oh, how much faster was it?
Yeah.
It was more on the order of 2, I believe, a little over 100%. I could actually share that in one way or another, but you can find the PR and the numbers for when we opened the PR for this in OpenSSL at the beginning of this year has a table that shows the official results.
Okay, thanks.
Okay, thank you, Daniel, for a great presentation. Thank you for everyone for attendance. So let's
Thank you guys, and thanks for helping me set this up to do remotely. I really appreciate it.